Water turbines are rotating machines that turns water kinetics and potential energy into mechanical works. Water turbines were invented in the 19th century and were widely employed for industrial power before the invention of electricity network. They are now mainly used to generate electricity. Water turbines are commonly seen in dams and are used to produce electricity from the potential energy of water. Water wheels have been used for industrial power for hundreds of years. Their biggest flaw is their size, which restricts the amount of flow and heat that can be harnessed. During the Industrial Revolution, scientific concepts were used to develop products. They also used a lot of the new materials and production technologies available at the time. A water turbine is related to the impact of a jet method. In fluid mechanics, a finite region of the fluid control volume is usually selected. The gross effect of the flow, such as its force or torque on an object, are determined. Their force can be determined, as in solid mechanics, by the use of Newton's second law.
For technology, a water turbine is based on the rotating motion of a rotary machine, such as a wheel or turbine, which transforms kinetic energy to mechanical energy, and the accompanying generator converts mechanical work into electrical output. One or more water jets are directed tangentially onto vents or buckets that are connected to the rim of the turbine, this in a Pelton wheel water turbine. The Pelton wheel works best in situations when the available head of water is high and the flow rate is low. For example, a Pelton wheel operating at 250 ref per min might generate roughly 900 kW with a head of 100 meter and a flow rate of 1 meter cube per second. If the head was only 10 meter and the flow was only 10 meter cube per second, the same amount of water power will be available, but different type of turbine would be required. The principles developed by Faraday are used to operate generators. He discovered that moving a magnet past a conductor causes electricity to flow. Electromagnets are created in huge generators by passing direct current through loops of wire wound around stacks of magnetic steel laminations. These are known as field poles, and they are positioned around the rotor's perimeter. The turbine shaft is connected to the rotor, which rotates at a constant speed. The field poles, the electromagnets, pass at the conductor's position in the stator as the rotor rotates. This results in the flow of electricity and the development of a voltage at the generator output terminals. Pump storage is a method of keeping water in reserve for peak period power demands by pumping water that has already flowed through the turbines back out a storage pool above the power plant at a time when customer demand for energy is low, such as during the middle of the night. The water is then allowed to flow back through the turbine generators at time when demand is high and a heavy load is placed on the system.
Construction process. Hydropower relies on the water cycle. Understanding the water cycle is important to understanding hydropower. The water cycle has 3 steps. Solar energy heats water on the surface of river, lakes and ocean, which causes the water to evaporate. Water vapor condenses into clouds and falls as precipitation, rain and snow. Precipitation collects in streams and rivers, which empty into ocean and lakes, where it evaporates and begins the cycle again. The amount of water available for hydropower production is determined by the amount of precipitation that drains into rivers and streams in a given geographic region. Seasonal fluctuation in precipitation as well as long-term change in precipitation patterns, such as droughts, can have a significant impact on hydropower supply. Hydroelectric power is produced with moving water. Hydroelectric power facilities are often situated on or close to a water source because the source of electricity is water. The quantity of accessible energy in moving water is determined by the flow rate and the elevation change, also known as the head from one location to another. Generally speaking, a hydropower plant can generate more energy the higher the head and the bigger the water flow. In hydropower facilities, water passes through a pipe called a penstock, pushing against and turning turbine blades to turn a generator and generate energy. Conventional hydroelectric facilities include run-of-the-river system in which a turbine is pressed, run-of-the-river system in which a turbine is pressed against the force of the river stream, a weir in the water course may be present at the facilities to direct water flow to the hydro turbines. Conventional hydroelectric facilities include: first, run-off the river system in which a turbine presses against the force of the river stream. A weir in the water course may be present at the facilities to direct water flow to the hydro turbines. System for storing water that release it through hydro turbines when need to produce energy after accumulating in reservoir formed by damming rivers and streams. The majority of hydropower plants in the US have dams and storage reservoir. Pumped storage water is pumped from a water source up to a storage reservoir at a higher elevation and then released from the upper reservoir to power hydro turbines situated below the upper reservoir in hydropower facilities, a sort of hydroelectric storage system. Nuclear or fossil fuel power facilities as well as hydro turbines may be used to provide electricity needed for pumping. They typically pump water to storage when energy demand, production costs, or wholesale electricity price are low and then release the stored water to produce power when wholesale electricity prices are relatively high and during peak electricity demand periods. In general, pump storage hydroelectric system utilize more power to push water to upper reservoir for storage than the stored water itself can generate. Pump storage facilities therefore have negative balance for power generation. Electricity generated by pump storage hydroelectric power facilities is reported as negative generation by the US Energy Information Administration.
Is and the which abundance of stream and river coming from the highlands due to its interior hills and mountains, and 149 locations for modest hydropower installation have been found through recognized in investigation conducted in 2010, which an estimate capacity of 28.9 megawatt, which around 50,456 megawatt weight. Malaysia has mostly used its considerable hydropower potential. The government stated in 2012 that it wants to significantly expand the amount of electricity supplied by small hydro projects from 60 megawatt in 2011 to 419 megawatt by 2020. The country's Small Renewable Energy Program (SREP), which promotes the development of energy generation from renewable sources, is consistent with development of small hydropower. The development of small hydropower in Malaysia is limited by a number of problems and difficulties. The biggest obstacle to this development is a lack of technical know-how and finance institutions are not experienced in evaluating the risks associated with small hydropower projects. In addition, it appears that Malaysia is facing a number of unique difficulties in the development of small hydropower, including flooding and overflow caused by heavy rainfall, ineffective design for removing sand and debris before they enter the turbine, challenging regulatory requirements for land acquisition and environmental impact assessment, and the possibility of water pollution during construction work as a result of logging activities. Federal and state regulations also apply to access to land and water. The success of small hydropower plants is also significantly influenced by the hydrological factor. Every run-of-river plant is subject to the same main limitation: seasonal variation in water availability, the danger of water shortage, and unforeseen water flow brought on by dry season, climate change, and river pollution make it difficult to assess the viability of modest hydro projects. Salinization has an impact of the efficiency of tiny hydropower as well, which lower the system total effect Alternatively, there is a need for in-depth study on sedimentation, including how to handle sedimentation more easily in small hydro system and improve sediment issue.
For conclusion, inventions such as the water turbine demonstrate how clever the human brain can be when it comes to extracting energy from natural cycles, such as water flow or sunlight reaching Earth from afar. Indeed, alternative research costs a lot of money, but it's an investment in the future where everyone will be looking for these alternatives. Water covers 71% of our world, and given how much water is used in electricity generation, it would be equivalent to not using any at all. That's all from us. Thank you.
For recommendation, first, the use of water turbine can be further expanded in this country. Uh, Number two, each person must exercise their understanding of the building industry in order to advance their technical knowledge and competence. And lastly, in order for the nation to progress and catch up to industrial nation, the government also has a significant role to play. In order to install advanced machinery like water turbines to facilitate Malaysia's electrical system, the government must balance the nation's economy.